the protocol which is IEEE C37.118, right, which is later on changed as 60255. So we have discussed the what are the different files uh, that is available for the synchrophasor devices, that is PMU, uh, and we have seen that there are different types of files available, right, starting from header file, configuration file, and so on. And then finally we discuss the what is the file structure of the PMU. So there we have seen that the whenever the any PMU wants to send the data to PDC, the PMU initializes with this command synchronization, right. Below this square box I have written some numbers which shows the word length, right, that what is the word length of each command. And then you have the frame size, right, which is going to decide the length, what is the IP address, ID code. And then these two commands, second of century and fraction of seconds, those are there, which runs by default. It is similar to like when you run any MATLAB or any other software, then time column by default comes. So similarly here also, some of the commands, whenever any PMU sends data in the form of packets to PDC, they by default it is there. And then you have the your original data which PMU wants to send, phasor data, right. This length may be different. Let's say PMU wants to send only phasor values of currents, or maybe voltages, or maybe both, or maybe voltage, current, frequency, or rate of change of frequency, or sequence components of currents and voltages, right. So this may change depending upon the requirement at the other end, PDC end. And then the final is last is the checksum. Checksum is just to avoid any error in sending the data by PMU to the PDC. So it is going to, what they do is, let's say simple best example is of checksum is, let's say you have one cycle data, continuous data, right, like this. So what you do is you are taking data at different instances. This is time and this is the magnitude, right? Magnitude of any quantity, voltage, current. So when you take data at different instances, then you just add it, do the summation, and if that summation value is greater than, let's say, some threshold, right? You decide that okay, what is the variation in load and all that. Based on that, you decide this, and if it is higher, then something is wrong. If it is within the limit, then that is okay. Whatever data is transmitted by PMU, there is no error. Some tolerance is also given. So this is all about the structure of the PMU, right? That how PMU is, when PMU sends packets to the PDC, then this is the basic structure, right, of the file. Now what we have done right here, right? So here we establish a setup which is known as cyber security testbed. So that contains obviously some real time simulator, right. You can use any type of real time simulator. We have used RTDS, right, because it is already available in the department, real time digital simulator. You can use OpenRT also, right. You can use Typhoon also. This all are the different types of real time simulators available in the market. Even you can use some lower version of simulator also, right, that is also available, so that you can use it. Now once you have the let's say RTDS, in RTDS you can do some modeling of the power system network, right, like you are doing in MATLAB, PSCAD, or any other software. The same way you can do in RTDS also. So by default it is known as RSCAD, right. It is a just a similar version of PSCAD. So if you know PSCAD, RSCAD is similar to that, right. So what you do is in RSCAD, which runs in RTDS, you can just develop your, let's say I want to develop a 14 bus IEEE 14 bus system model. So then you just develop the system like you are developing in other some software, and then you put the PMU. So those PMU which is available here in RTDS itself, that is known as software PMU. Those are not physical devices, right? Those are, let's say, like you are placing load or like that in any simulation. Those are not physical loads, right? But you are using in simulation. So here also you can use some software type of PMUs which can acquire the data. And whatever data, let's say, you have acquired, what you do is you just there are different ways, right? I have shown here. Let's say if I have software PMUs, then whatever the output of that PMU, that should be supported by the compatible cards. So that is normally done by GTNet card, GTNet X2 cards, that is what they call it. And this cards I have mentioned here, it is a giga transceiver network card, right? So basically whatever software PMUs are there, they can send the data through this card to your network switch, right? So everything whatever you want to send, let's say PMU wants to send the data to PDC, right? This is my PDC here, right? So then that should be sent through network switch, that is sure, right? So one way is you use software PMUs. Let's say you don't have hardware device, hardware PMU, then you use ready-made whatever is available inside RTDS. You send it the data of PMU to PDC through network switch through this card, right? This card cost itself is roughly around 12 to 14 lakhs, right? If you purchase it. Now, this is one way, right? Other way is, let's say I want to use physical device, physical PMU, because it is already available in my lab. Let's say this PMU, right? So then what we do, whatever modeling you have done here, you just take some data, right? Then you give it to some analog card. It is known as a giga transistor analog output card. So it is going to convert all your digital values into analog values. But when this conversion takes place, the values magnitude, that is very low. So then you need some amplifier, right? So we have Omicron based amplifier, it is available. So we use that, and then whatever the output, whatever PMU is there, you can give it there, and from that PMU you can transfer it to PDC again through the network switch, right? So that is another way if you have physical PMU in your lab. So one is software PMU, another is, let's say, your physical device, physical PMU. Now sometimes somewhere, right, I observed, I don't know whether utility people correct me, you have the relays which are PMU enabled relays, right? That means the relay or ID will act as a ID or relay as well as PMU both, right? This I have seen somewhere in US, Texas region. So there you have a relay, right? So what you do is you again take the digital input, means whatever relay output is there. If I want to do reverse process, relay output in the digital form, you can use this GTDI card, giga transistor digital input, and back you can give it to RTDS also. So this is how you can complete the loop also, right? And some of the this lower path, that is used just to synchronize your physical devices, right? So that time stamping that can be done. Time stamping means, what is the meaning? I'm utility people will know. Let's say I have the two bus here available, right? I have one bus here, another bus is at very far end, right? Let's say 100, 200. Now you are acquiring the data here, right? Let's say 3i plus 3v, and here also you are acquiring the data 3i plus 3v. Now this two data, that is you cannot acquire at same time instances, right? That is there. And because whatever data you acquire at, say, at some time distance, let's say t1, whatever data you acquire here, there has to be some time difference, t2, right? Now t1 and t2 both are not same, but this is known as unsynchronized measurements. But here your PMU, whenever they acquire the data, they acquire the data at same time instances, right, which is known as time stamping. So here they acquire the data at same time instances using this GPS, right, GPS clock. So that the whatever the, or even though they have not acquired, then time stamping that can be done by PDC also, right? They are going to match the time instances. So this is there. So whatever the data you are sending to PDC or let's say some controller, if it is there, then you have to send it through the network switch only, right? And so that means why network switch? Because whatever, whenever attacker is there, attacker will always try to attack on this switch, right? Because all the data, whenever you are either software PMU, hardware PMU, or any meter, any ID, you are sending through this switch. So always attack that can be done on the switch only, right? Okay, now how the attack can be done, right? What we have done. So here we have considered one example, right? Let's say I want to send the data from source to the destination. So obviously I have to send it through switch, right? Switch is required, and that switch I am using some software, right, so that I can do some attacks on that. Now here as a source we have considered, let's say, or instead of PMU I considered GTNet X2 card software PMU, right? Whatever data is sent, it is available here, right, from RTDS. And the destination I have considered PDC. So PMU wants to send the data to PDC, it is sending through network switch, right? And we have used this NetSim. You are already aware it is a network simulator and emulator, right, through which you can just do the cyber different types of attacks. Now this switch we have considered is a SEL based network switch. So it is going to support the both the Ethernet ports as well as fiber ports, right? 4 fiber ports and plus some Ethernet ports. So this switch you can consider that it can act as all your in between intermediator, right, where you can send the data maybe from PMU to PDC or any other smart devices. Now with this we have performed this different types of attacks, right? Let's say delay attacks, we have given the delay, then denial of service attack for some period of time, let's say 5 second, 10 second, the data is not available. Packet error attack, some errors in the packet, that also, that means your from source you are sending, let's say, 80 packets, but those packets all 80 that is not going to reach at the destination. Some of the packets they are dropped in between. So that is some flooding type of attack, you are continuously sending the request to the destination without getting acknowledgement from the destination. So that type of attack is also there, right? Now if we just look at the delay attack, so then this is my source and this is my destination. I am going to send the data from source to destination through my network switch. So what you can do, you simply add here some delay. Let's say I have added 50 millisecond time delay, and when you add this after this red line, you can see that the time which was earlier 1 second, now it becomes 51 second, right, from here this point. So this is just an example, right? How you can do, you can do it in using Python also. You can do it in some other software also. Let's say I want to create denial of service attack. Okay. So what we have done, again I want to send the data from 1 to 2, source to destination through switch. So then what I have done, I have, let's say, I have dropped all the other packets. So none of the packets that is available for some period of time, right? Earlier your source is sending the packets to destination from here to here, but later on no connection is there, source is not sending any packets. Same way you can do some other type of attack, like let's say packet error attack. So here I have shown the source is sending 82 packets at the destination, but at the destination you are receiving only 74 packets. So in between somewhere 8 packets that is dropped here. So from here to here packets that is transferred, and again there is a dropping of packets, and again you have the further the packets, you can again it is continued, right? So this is also similar type of attack. Let's say some flooding type of attack, as I told you. So whenever PMU wants to send the data to PDC, PMU first send the synchronization request, right? The first structure we have seen, file structure. So then the BMU has to wait uh, till the PDC sends acknowledgement. Yesterday, Professor Sidhu explained handshaking, right, between server client server communication. So once they send the request, then the request is received, then the data transfer that is started. So same way here also, that also you can do it. So here you can see that the no connection, right? If you have such type of attack, that means here attacker is continuously sending synchronization request without receiving acknowledgement from the other side destination. So then you see that there is no, it's a connection timeout, even though you start continuing sending the data. Maybe we have run for 1 minute, right? So you can do it for higher time also. Same way, here also some ICMP flooding attack also. You can see that there is no actual packet flow between source and destination. So this is just an example, right? This you can do in any language. Now, what we have done using this thing, right? This setup. So here, what we have done, we have used the, let's say, GTNet X2 card. It can act as a software PMU, and we have sent this data using 240 frames per second to the PDC, and this we have done using C37.118 protocol, right, which is synchrophaser protocol. And the data which PMU has transferred, that is the frequency, phase angle, and this is the data frame, right? You can see that. Okay. So this is just an example that how whenever the data that is to be sent from one side to another side, source to destination, then how it looks. Now, if you just look at the, let's say, the capture data, right? How the, let's say, if you just captured the data here, if you just look at the window, then this data looks like this, right? All the phasors. Now you can see here the phasor one, that is your VA, right? You have some magnitude and angle. Then you have VB, again magnitude and angle, VC, then IA, IB, IC, V1, V2, V0, I0, I1, and maybe if you have frequency here, it is not there. So this data the PMU can send it, right, using this C37.118 protocol to the PDC. Okay, now the same thing, instead of soft, we have also tried on the hardware setup, right? So few types of attack. So let us see that how it looks like this. So when you have, let's say, you have given some deliberate delay, right? So if you do that, some deliberate delay, then after, if you see here, you have see the actual waveform, the magnitude of VA in kV and the current, a phase current in kiloamps. So this is scaled, right? This is obviously scaled. So then after some delay, after some time, there is some delay, right? It is always there. So this type of attack that you can easily do it. Then you have, let's say, denial of service attack. So here what we have done, you can see that after some time, the data for, let's say, 10 seconds, it is 10 to 20 seconds, the data that is not available. And again after 20 seconds, you will have the data. So from up to this window, let's say here, for both voltage magnitude and current magnitude, the data that is lost, right? And again the connection is established, and again you have the further the same thing. So this is nothing but, we can say that it is a denial of service attack for this 10-second period. This can be variable, right, depending upon the attacker, how attacker wants to do the attack. This is the different scenario of replay attacks, right? So here you can see the waveform where this waveforms, that you can see the waveforms captured at PMU, right, source. So it is the VA, IA and IB, right, one phase voltage and the two phase IA, IB currents. And below side, the another three waveform, right, just below this, you can see that it is the waveform captured at the other side, right, destination side. So here you have again the VA, IA and IB, similar that. Now if you just look at, this is let's say the case of, let's say, first case we consider a replay attack using single packet, right? So one packet I am replaying. So if you just look at, then after some time, PMU is sending the correct data, but at PDC you can see right here that it is replayed like that. So single packet. You can do it for, let's say, multiple n number of packets also, multiple packets you can replay it. So that also you can see that PMU is again sending the correct data, but here at the destination your PDC that is not correctly analyzing that things, so that data that is replayed, right. So this is how the attack can be made on the other side, at the other side, PDC destination side. You can also create, let's say, disturbance at the bus, but replaying the pre-recorded data at PDC. So if you just look at here, again, these are the PMU waveforms, and again, these are the PDC waveforms. So here you see that sometimes after some time there is an abrupt change right here, but still here you see that what is the change in the waveform. So that type of attack also you can create. And the fourth one is the replaying a fault condition at PDC during a normal scenario of the power system network. So that other way, right? The third one just exactly flip. So here you are having the correct data, but here your PDC is not receiving the correct data. So this is how you can create different multiple types of attacks or multiple type of scenarios in replay attack, one particular type of attack. Okay, this also I have, this is an example of the another type of attack known as false data injection attack. So what you are doing, that you are adding some incremental value in the your actual data, right, which is transferred by PMU to PDC. So here we have shown the incremental change of 0.01%. You are adding this, and then you can see that this is the output. Same way here also you add some zero injection. So earlier you have this value, then again it becomes zero, again you have some value, again it becomes zero, like that. So this is known as zero injection. So you are adding something, right, some let's say some different value which is not, you are manipulating the data basically, right. So this is that this shows the that type of attack, and you can again try constant value injection, zero injection, incremental and decremental changes, random injections. So that multiple scenarios you can create in false data injection, right. So this is basically when PMU is transmitting or transferring the data to PDC, whatever the actual data is there, you are trying to manipulate those values, numbers, right, phasor, so that your phasor values are not correct, right, basically. So that is this is this example of that type of attack. This is also now see earlier what we have shown, that is related to the your IEEE C37.118 synchrophasor protocol. Now you can also create, let's say, delay and DOS attack on DNP3 also, SCADA system, right, where you use different protocol. So you can create, right, here you can see this there are three categories I have shown. So in first category, though I have mentioned here, delay attack, DOS attack, and prolonged DOS attack. So here there is a delay, right? You can see somewhere some delay is created, right? And then you are getting the, that means when PMU is transferring data to PDC, you add some significant delay, right? Using DNP3 protocol. This is for SCADA system. Same way here also you can see that it's a DOS attack. So for certain period of time, again the data that is not available, again you re-establish the connection, and again that this is that means the data is available. And then third one is the prolonged DOS attack. That means for certain significant period of time, again the data that was not available. So this is also this type of scenario you can also create in some other type of the protocol, that is DNP3, right. So whatever the attacks we have considered, right, like starting from delay attack, then DOS attack, and false data injection attack, replay attack, all this type of attacks we have done on C37.118 protocols. Similarly you can do it on DNP3 also, right. So that's why you can, we can see that we have not done on IC 61850, right, that we have not done, but however one can do it, that also. So for these two protocols we can say that these protocols are not meant for any cyber security purpose. That means anyone can attack it. There is no, let's say, by default something is not given inside this protocol, right, it is not covered, right, basically they are not cyber resilient. So then that means something is required so that we can detect or avoid this data. So some solution that is required. So then this is also another false data injection attack which we have done on DNP3 type of protocol. So here I think you can see this is the healthy data, and these are the different three scenarios of false data injection. You increase the magnitude, you decrease the magnitude, you increase and decrease the magnitude of manipulate the your values which is sent, right? You once one time you increased it, let's say in second scenario you decrease it, and third scenario you do it both way, increase and decrease, so that you can do it, right? Now the question comes, sorry, this is not that. So this completes yesterday's part, right? That is what we have considered started using C37.118. Now after this, the next part is the solution part, right? What is the solution? Let's say some attack is there, either delay, DOS, false data injection, or replay attacks on either C37.118 or DNP3. Then what are the solutions? Probable solutions, right? I cannot say these are the only solutions, but what are the probable solutions? So that we can consider, right? Oh, next. Okay, so then I think let us see what are the solutions of this, right? Once attack is done, so how, what we have to do, right? So the thing is that there is no such solution exist. So what we have to do when attack is there, right? So the first task is the operator has to identify that there is an attack, right? There are various conditions, various scenarios, various disturbances exist. So the first task is that the operator has to identify this is an attack. It is not a healthy or normal condition. It is not a fault scenario also, because fault and attack both are different cases, right? So first is the detection of attack, number one, right? The second is, once you have detected, depending upon the type of attack, let's say if you have DOS attack, where the for significant period of time, let's say data that is not available, PMU is not sending data to PDC, in between it is lost, right? So then you have to reconstruct those data, right? That is the only thing way how I can mitigate the against the attack. Now, whenever the connection, let's say PMU is not sending the data to PDC, let's say for example, PMU is sending the data to PDC, for example. Now, in between, let's say in DOS attack also, let's say for some period of time, let's say everything is lost, right? That is what I have written, right? This type of attack makes the machine service network not accessible, right? For certain specific period of time, 1 second, 2 second, 5 second, 10 second, depends, right? And this type of attack usually occurs because of overwhelming of traffic, right? That means you want to, let's say it is a basically a congestion, right? In electricity market, you studied network congestion. So when you try to send more data through a specific line or medium, then such type of event takes place, right? And there are of course different types of DOS attack also. We are not going in that detail, right? Though I have mentioned it is distributed denial of service attack, application layer, volumetric protocol. There are different types of attack, right? Ping, death, and so many are there. Now the thing is that so that means whenever there is a DOS attack, we know that for certain period of time, let's say 2 second, 5 second, data that is not available. So first we have to detect that it is a DOS attack. Once we have detected, then we have to reconstruct the data for that period of time during which the data that is not available, right? That means PMU is sending the data, but PDC is not receiving the data for that period of time. So we have to reconstruct. So detection and reconstruction, mitigation, what you call, that is to be done using some method or technique, right? Maybe either you can use some statistical methods, or you use some other methods like AI or ML based methods. It depends, right? So what you are going to use. So let us see one example, right? How we can detect the DOS attack and how we can mitigate it, how we can reconstruct the loss value or loss data also. Now this is usually done by 4 ways, right? The first is that means when I want to carry out the detection of DOS attack and reconstruction of data also during the period where the data that is not available, then it can be done. One of the way is you can use, let's say, this 4 block. It can be 3 block, it can be 2 block, it can be more than 4 blocks also. It depends, right? So first is that we have to prepare the data and we have to pre-process the data, right? Whatever data is available, you have to prepare it and pre-process it. Then you have to select some features, so that this is based on AI/ML, right? You can use some other technique also, statistical one. Statistical is far better if you use it, right? Because there is no guarantee of AI/ML technique. Whether it gives today, it is giving good result, it may not be sure, you may not sure that tomorrow or after 10 seconds it will give you the correct result, right? It is not sure, but this is one of the way, right? I am just giving you one case study that this is how you can detect and reconstruct the this type of attack. Then you have to detect it and classify it using some ML models or some other technique, and then you have to reconstruct the that data, right? That is there. Now this block, first block, that is very important. If you just look at this block, yeah. So the first part comes, as I told you, when PMU sends data to PDC, this data is not sent by default, right? So PMU is going to add encryption, and then at the other side, PDC, when receives the data, PDC has to decrypt it, right? That is by default, it is there in PMU, right? I don't know PMU. We have a PMU of SEL based. I don't know whether any other manufacturer is there who is selling the PMU. I think utility. Huh? ABB is there, but I don't know whether the ABB is selling the. Have you purchased it? Acha, it is there. GE is there, but GE has collaborated with one company, VZMax. So it is not the product of GE, right? It is the product of VZMax, right? I don't know other company. Maybe in US it may be there. I don't know. Okay. Now the thing is that when you let's say when PMU sends the data, obviously, then I told you that first you have to it encrypts, and then at the other end you have to decrypt it. So that involves few steps, right? Few algorithms that is involved in that. Let's say I have captured the data at Wireshark. Let's say this frame, right, 198th frame. So if you just look at this data, right, at Wireshark, then it looks like this, right? This frame, right, 198 frame, and this looks like this. Again, the same, right? Your phasor value VA, VB, VC, V1, IA, IB, IC, I1, V0, right? V2, I0, I2, like that. Frequency, rate of change of frequency, and it looks like this, right? This data, which is encrypted. So if you just look at the here raw data, then the raw data looks like this, right? Now here in the raw data, how you can identify? So there is a, you can see the symbol /x here and /x here everywhere, right? You can see throughout the data. So the first, whenever you have the /x, first one, right? After that, you can see there are some digits. So I have mentioned here the first 2 digits, right? That is after this /x, you have to take it as it is, and third one you have to convert it into this form, right? That is what you have to do. Same way, whenever the next /x comes, you have, let's say, these three values A7 and dollar sign. Then A7 you take as it is, and again this you convert in the again this form, and this thing you have to repeat throughout this window, right? This is the normal what SEL is doing, right? Maybe some other companies they are also doing the same thing, right? So slash x, between two slash x, what you have to do is you can see first, after that the three digits, two you take as it is, third you convert it into ASCII. The next one, again you have the digits, you this take as it is, the this sign you convert it into the ASCII. Now when you do this, uh, then this raw data, if you do that, it looks like this, right? You can just see this data, right? It is in hexadecimal format, and this red color, red values, that shows your data header. I told you, right? Something is there when you generate some files. The time column is by default it is there, along with some other important values, voltage, current. So these are the data header which shows source and destination IP address, right? Port number, protocol type, packet length, etc., which are there in the file structure of PMU. You hope remember, right? The SYNC, then you have the IP address, IP port, and all those things, right? Fraction of second, second of century, all those things before the data starts. So this green color, that is your actual data, right? Which contains timestamp, phasors, frequency, rate of change of frequency, right? So this is your actual data, right? Which PMU wants to send to PDC. And once you have this, then what you have to do, sorry, this data which is in hexadecimal format. So now you see from Wireshark, when you do capture the data, it is in raw format, not readable form. You convert it into hexadecimal format, right? And then again you use some algorithm. So this algorithm, when you want to convert this data which is in hexadecimal format into your actual phasor value, then you have to use this algorithm, IEEE 754 conversion algorithm, right? And if you just check this thing, right, which was our original data, if you look at this one, right, then this shows this value, your A phase voltage phasor, right? So this is real part and this is the imaginary part, right? And once you add these two, then finally after using this 754 conversion, you will have the final value of phasor, that is VA, some magnitude, kilovolt, and some angle. This is in volt, right? That is there. So this you have to do for all other data, right? Entire data. And once you do that, then you will have the VA, VB, VC, IA, IB, IC, whatever data PMU wants to send, right? And the same process that is to be done at PDC level also, right? So PMU, that is going to encrypt it, and then PDC, it has to decrypt it at other end, right? So this completes the one part, right? That is what we are saying, this part that is completed, right? The encryption and decryption part, right? This you have to do whenever you have PMU, physical PMU, then you have to do this process, right? Or PMU internally it is doing this thing. Then after that, the feature selection second block comes in picture, right? So here we have used some one technique known as principal component analysis, very well known technique in the statistical side, right? Statistical method, I can say. So what PCA does, so it is a basically a feature reduction technique. Let's say I have, for example, 10,000 data, right? And that data contains, let's say, 20 features, right? Maybe you have some voltage, current, magnitude, sequence component of voltage, current, mean, or anything, right? And I want to, let's say, reduce it from this 40 type of features to, let's say, 10 features. So then you have to use such type of technique, right? Principal component analysis type of technique. So basically what PCA does, it is going to reduces the number of input features or variables, right, in a data set which is lower form, but preserving your original information. There is no loss of original information. That is more important. So whenever you use any feature for feature reduction, whenever you use any technique, you have to see that your whatever the original features are there in overall earlier data set, that should be retained, right? That is very important. So basically it is going to transform the features into the orthogonal, you can say uncorrelated features known as principal components. And then once you do that, it is going to rank in the order of variance, with the first component capturing the most variance, second one that is the second one, third one that is the third, like that in the descending order. So let us see how this is done. So for example, I have my original data set, right? Let's say that data set contains 12,000 values and it has a 59 features. How this 59 features look like? Let's say my data set is like this, right? And this 59 features, that is, I have the data payload, phase voltage magnitude, phase voltage angle, line currents, right? Line current magnitude, angle, sequence current, and so on, right? So all this you can see change of current, change of voltage, change in sequence voltage, change in just we have added, right? So you have this values, you have total 59. So you have 12,000 points, right? 12,000 rows, and I have columns, that is my features, that is 59, right? This is my original data set. Now let's say I want to reduce it, right? This 59 features into some, let's say 9 features. You can reduce it to 5 also, 10 also, it depends, right? What application you are doing. So we have used PCA. Now what does the PCA do? So PCA, which is a method, as I told you, it is going to reduce the number of features from, let's say, X value to Y value. So then inside this, they are doing some calculations, and those calculations are based on some statistical formula, obviously. So they calculate covariance matrix, then they calculate eigenvalues and eigenvectors, and then they find out the variances and cumulative variances, right, of all eigenvalues which you have calculated here. So earlier, when you have 59 features data, 12,000 remains same. Your covariance matrix, that is of 59 cross 59, when you convert it into eigenvalue and eigenvectors, it becomes 59 cross 1 and 59 cross 59. And then when you calculate it further, variance and cumulative variance, it becomes 59 cross 1. How it looks like this? So if you just look at this thing, right? So then the steps involved, that is like this. Now before we just look at this, let us see what are the steps involved. So here, let's say I have a data set, right? 12,000 something, right? I have this data set available. So what I do, I standardize this data set, right? Using this formula, right? What is this mu and this one? What is mu? It is a mean. This is a standard deviation, very well known formula, right? We used in Excel. So you use, let's say you apply this, you get this value, right? X standardize, STD means standardize. You can take any value. Then you calculate covariance matrix, right? As it was shown earlier in the PCA block, right? So covariance matrix you can calculate using this formula. It is a standard formula where you can use this XTD transpose and XTD. This it is already calculated, and this you have to divide by n minus 1. What is n? It is your total number of data sets. I have written here, right? The division is due to the concept given by Bessel's correlation. It's a someone, right, who has given this, and this is done. Why this is done? This is done just to, so that the whatever the output you are getting, right, that is unbiased. It is not biased, right? That's why it is done. So this is already so that whatever estimation you, because ultimately what we are doing, we are estimating, right? It is not the correct value. Like in load flow, we are estimating the value of V and delta, right, by iterative techniques, whether you use Gauss Seidel, Newton Raphson, fast decoupled, whatever it is, right? Each has its own advantage and disadvantage. So this is also an estimation technique. So whatever estimator you decide, you have to do somewhere here. There are various ways, right? One of the way is you simply divide this by the and total number of data sets minus 1 points, right? So that your estimation becomes uh, reasonably accurate. I do not say it is accurate always, reasonably accurate, right? So once you have the value of C, then you compute the eigenvalue and eigenvectors. This you can compute using this equation. C minus lambda I is equal to 0. C is known, I is identity matrix, lambda you can calculate, right? And the other one, that is eigenvalues, you can use these equations. And once you do that, this gives you eigenvalues 59 cross 1, this gives you eigenvectors again 59 cross 1, right? These are the way. These are the simple equations. So this you can calculate. And once you do that, using eigenvalue and eigenvector, you calculate the variance. So variance you can calculate using this formula, right? Lambda is already known. So once you do that, now here, once you have the variance, you can go for the cumulative variance, right? Now what is cumulative variance? So cumulative variance, let's say you have calculated the variance in descending order, for example, using that formula. So this is, let's say, my variance. I have not shown all 59. Let's say only up to 9 or 10. Now cumulative variance is nothing but, you can see, first it comes as it is. The second one, it is addition of these two, right? That is here. The third one, it is addition of first three. Like that you calculate the cumulative variance. And I stopped at 9 value, because after this you see that this value that becomes reasonably constant. So there is no requirement of adding more number of features below this. You can stop at 8, 7 also, it depends, right? It depends on your data set, application, and so on. So So once you do that, my original data set, which was 12,000 by 59, now it becomes 12,000 by 9, right? That is, we have reduced without impacting the originality of my own earlier or original data set. Now once you have this data set, what you have to do is you have to scale it down, right? So that it comes between the range of 0 and 1. So that you can do using this formula. Again, this is a statistical formula, well known. You can calculate maximum and minimum value of the data set. So once you do that, then what you have to do, let's say randomly we have considered several classifiers, right? Decision tree, then KNN, random forest, GB classifier, Gaussian NB, so many things, right? There are, if you type in Google, you will find n number of classifiers. This is just we have considered, right? You can consider more different also. Uh, Now you can see here, if you just look at, we have considered several, let's say some indicators like accuracy, F1 score, recall, all those things, and time. Now if you look at this last column, right? This is without PCA, and this is once you apply the PCA. After that, you see that there is a significant reduction in time, right? And that is much more important when you use any AI or ML model. Time is much more important, right? Because other parameters you look at, it remains almost same, right? There is no significant difference, right? Marginal difference. So the only difference you can notice, that is here, right? Uh, so that you can consider. This is just for an example. Huh? It is not that it is always decision tree gives you best result. It is not like that, right? Okay. Now the what are the types of DOS attack we have considered there. So here you can see that I have shown the voltages and currents, right? This is the current magnitude and this is the voltage magnitude uh, at PMU, right? And below this again the same voltage magnitude and current magnitude that is received at PDC. And then we have done, let's say, some fixed rate of DOS attack for, let's say, 10 second the data, though PMU is sending the data, right, this data, but at PDC for 10 second data that is not available because of DOS attack, right? And same way you can try multiple also, right? Maybe sometimes 4 seconds, 2 seconds, 10 seconds, let's say data at PMU is sending the correct data, but PDC that is not receiving the correct data because of DOS attack. Now you can also try this TCP and UDP, right? Both are different, right? You can see this protocol TCP and UDP, that is different. Now here at this side you can see that we have done some let's say some drop attack using the this shows the your UDP as the protocol, where you have the you are transferring, PMU is transferring voltage magnitude and current magnitude, right? And here you can see that you are seeing the same thing, right? When PMU is transferring to PDC the voltage and current magnitude, but using TCP protocol. So this I have just for knowledge I have written that what is the difference between TCP and UDP protocol, right? Just the major difference is TCP requires handshake like client server before sending the data. Here it is not required, and that right. And even the you see some other parameters like reliability. This ensures proper delivery. There is no guarantee of delivery. Here the speed latency is there. Here it is less compared to that. Packet ordering, this maintains where there is no nothing is there mentioned, and error detection and correction is there. Here you can it can do it only detection, and that you can also observe here, right? Can you see that here some gaps you can observe, right? When you use the UDP protocol, here it is not there. So that we can say that the TCP protocol is better than UDP. This is just for okay. Now we have also tried one more thing, jitter. Now what is jitter? So yesterday I when I explained the C37.118, I explained you what is latency, right? What is the I have mentioned here. What is latency? The total travel time of the packets when it is generated from source side and when it is available at the destination side. This is latency. Jitter is something different, right? It is the variation or inconsistency in the travel time from one packet to the next. So basically it is nothing but the difference in travel time between between the multiple packets, right? So this is there. Now sometimes you cannot say that even though let's say my whatever protocol I am using, it has low latency, but it can be it may have high jitter, right? That is also possible. So this is it is not that okay my whatever protocol I am using, it has a low latency, but it may have high jitter, right? Inter packet travel time, that may be different variable. So that also we have tried, right, here in the attack side. So what you can see here, we have tried this jitter on healthy date and some let's say attack scenario. On the x-axis, you can see the packet index. Y-axis, it's a time because it's a inter packet travel time. So this is in millisecond. So here you can see the window is only 4 millisecond, but here we have tried it up to let's say 25 milliseconds. So somewhere you can see some big jumps, right? Transients, which is nothing but your jitter, and that we have tried here, right? In the table you can see, if you just look at for that jitter, healthy and attack scenario, then mean standard deviation and the maximum value, you can observe this value, this 3 and this 3, there is a huge difference, right? Specifically this two. So you can, let's say if you consider I have a jitter greater than millisecond, difference between inter packet travel time is more than 2 millisecond, this is less than 10%, but in attack scenario it is like this. So this you can also consider. Now what we have done, oh, this we have created intentionally, but yes, attacker creates it intentionally. It may possible, right? Okay, now what we have done, this is again the detection of DOS attack. So once we have done all this attack, we have to detect it. So for that, again we have considered various classifiers, right? Here it shows again, as I told you, you can consider, we have considered decision tree, KNN, random forest, gradient boosting, and so on, right? And then we have again calculated several parameters starting from accuracy, precision, recall, F1, training time, detection time, and rank. Rank, that is okay. We will discuss later on. So this is what we have calculated right here. And once it is done, then you can see, okay. Now the question is here you have to let's say I have the total number of data available. Now what you do in AI or ML, any algorithm, you have to do the training and testing, right? So there are different ways, right? You, let's say you take 60% of the total data in trainings and remaining in testing, 70%, 30%. There is no such rule exist, right? Sometimes reverse is also good. According to me, you have to consider that classifier is the best one, where you take only 20 or 30% data in training and remaining 30, 60 or 70% data in testing. So that would be far better. But anyway, if you test like this, then the accuracy is very bad, right? And then someone may comment why the accuracy is very bad. So that's why normally nobody is doing like that. Now here what we have done, so what this 60 40 70 30 I told you, this is known as random splitting, right? The random splitting. But when you have time critical data, right, there random splitting does not work. So there you have to go for the chronological split, right? So this we have done using, so what we have done, you have some, let's say, total number of data that is available here. So what you do is you just identify some points, and before that point whatever data you make it in training, and after that data you go for the testing. So it is known as the chronological splitting of the data, or this is how you can split the data and then do the training and testing part. This is one of the way, right? There are many ways that how you can do that. So this is what we have done. And after that what we have done, uh, we have, just to increase the accuracy, right, we have used some classifier. So it is known as the meta classifier, right? So meta classifier, what we have done, let's say I have original data set, some value, random, let's say 38,000 data sets I have divided in several segments. Let's say I divide this data set by 1,000. You can make it 2,000 also, 3,000, it is up to you, right? So here if I do it, I have 38 segments, right, where in each segment 1,000 data sets are available. Then I added some statistical features, right? What are the statistical features? Let's say mean, standard deviation, kurtosis. Then you can add some more, right? So this type of variance and so on, right? Whatever it is, so that you can add it. We have you considered 5 only, and this let's say I have considered only one, let's say mean, for example, right? So I, this 1,000 data set I have calculated mean value, right? And then I have done the training with this uh, classifiers, whatever classifiers you are taking, let's say 9, 5, 10, whatever it is. And once you do that, then you calculate the rank, right, which we have calculated here, right? Rank for each classifier, and you have to consider that classifier which has a highest rank, right? So that I have written here. F1 is the F1 score which we have calculated here, right? This one, this column, and below is the detection time. So higher is the detection time, your rank is lower. This is how it works, right? Better is the F1 score, better is the rank. This is how it works. That's why F1 score, it is in numerator, and detection time, it is in denominator. And this some parameter tau we have added just to avoid the divisible by zero error. Otherwise sometimes it may possible that you may end up with divisible by zero error. So this is how you can calculate for all segments this type of rank. And this rank, right, whatever top rank model, each for each model you calculate highest rank, that, and this statistical parameters you are giving to some classifier, again different classifier. Here we have used support vector machine, and then you deploy it in real time. So earlier when you have not done anything, earlier your whatever data, it acts as a base model. And whenever you take, let's say after 1 month, fresh data are available real time, again you calculate all these things and again you compare with your base data. So here, whenever it matches with your original base data, that classifier, let's say it matches with the, let's say for example, the this value, right? For example, so then it takes that statistical, let's say mean value, it matches with, you calculate again the mean value, and it matches with, let's say this classifier. Then it takes that value, right? And then it calculates the concept drift. Concept drift is nothing but it is a ratio of Euclidean distance, right, between the same classifier, right, and the denominator different classifier, like that. And if this value, right, this value of Tx, if it comes greater than 1, then you can say whatever classifier you trained earlier, you are using 1 month ago, that remains as it is. If it is less than 1, then it shows that retraining is required. Then again you have to retrain your algorithm. So that is what we have done. And if you do that, then after that, if you just look at, we have used let's say 24 predictions for decision tree. It gives 100 accuracy, whereas the other two classifier which comes, they have misclassified the two events for this classifier and one events for this classifier. So again the accuracy, that is not good, right? So this is how you can just carry out the detection of DOS attack. This is going, this shows that how we can detect the DOS attack. Still the reconstruction of data during that 10-second or 2-second or 5-second, that is remain, that is not there. That is what we have not considered, right? I think I stop here because it's a time, so that otherwise our next session that is delayed. Any questions? This will continue tomorrow, right? Reconstruction part.